Okay, we have written the integral from 0 to pi over 2, 1 over 1 plus 2025 tan squared x dx. Okay, to get started with it, the first thing I want to notice here, 2025. This thing is going to be very nice because this is the same thing as 45 squared. And so what I'd like to do right now, rather than deal with 2025, let's just generalize this for any square number right here, any constant here. And so we'll just call this a squared, where we know when we come back and we want to get our final solution, a is going to be just equal to 45. And if you want to know where I got this problem, there was a suggestion in the comments by Ashish that we do this with, it was written like this, I think, a tan x all squared. What I didn't realize is this here, this is actually supposed to be arctan. So I don't know how to do that one, or I haven't looked into it yet, so maybe I can do it, but I haven't even tried that. So I did it a totally different way. I was looking at a different problem. It's still a pretty interesting problem, especially because we get to use 2025 in it. Although I think with arctan it would be a lot harder. This is not going to be that bad. So to get started with it, what I want to do is the thing I always like to do, and that's multiply in by 1 with secant squared x over secant squared x. This works really well when we've got like tan squared, because then we can hopefully do a substitution. So when I rewrite this, I'm going to leave it as secant squared in the numerator. But in the denominator, we can use the identity on this. Secant squared x is the same thing as just 1 plus tan squared x. So I'll multiply it in this way in order to set up the substitution. If you did end up with a secant squared in the denominator in some cases, you just try to change those all over to tangents, and then you have the substitution. So we'll do u equal to tan x. Du is going to be just secant squared x dx. So we substitute, and when we update our bounds, tan at pi over 2 is going to infinity. Tan at 0, that's just 0. The whole numerator is the du, so we end up with du over 1 plus a squared u squared times 1 plus u squared. But now with what we have here, it's perfectly set up for me to avoid partial fractions, or you could do it out, but I'm going to still avoid it. So how I'm going to do it is I'm just going to set up the cancellation I want. If I create both these terms in the numerator, what we have here, if I break this into two integrals, we're going to get all the cancellation we want, but the only thing is it doesn't quite work right now. We need to get it where this whole numerator is just equal to 1. Now one thing I can do, if I multiply in a squared here, notice a squared times u squared is a squared u squared. It's going to cancel with this. Multiplying it out, the numerator is going to become a squared minus 1. I don't want to change it, so let's just divide that off in front. So now, doing it this way, if you multiply it all out, the whole numerator is just 1. And so now let me just take this and I'll rewrite it. We'll split it up into two integrals, breaking it on the minus sign here. And then at this point we get cancellation, 1 plus u squared over 1 plus u squared. This here is going to cancel with this, just leaving a 1. Now in this integral here, when I rewrite it, what I'm going to do is, let's factor out an a squared. So what's going to happen, we have a squared du. I mean, we could bring it up front, but I think this is maybe a little nicer. I don't know. If I factor the a squared out of the denominator, this 1 becomes 1 over a squared. Then this just becomes u squared. And then for the second integral, all that we have left is this. This is exactly the arctan integral. So what we have over here is going to be just arctan of u from 0 to infinity. But over here we can cancel a squared with a squared. And then with this thing squared, thinking of it as like 1 over a all squared, then this is also set up for the arctan formula. So let's see what we have. We've got the constant out front. Then here, using the arctan formula, we flip this, so it's going to be a arctan au. We'll evaluate them together, so then this part's going to be just arctan of u, and we're evaluating from 0 to infinity. And now we're in good shape to finish this off. Now notice arctan at 0 is just 0, so we don't have to worry about that. And the constant here is not going to matter, because when you're evaluating at infinity, we're assuming here we always want a to be greater than 0. So what's going to happen when we plug infinity and we get pi over 2? So what we have, we're going to have 1 over a squared minus 1. Then inside here, this is going to become a pi over 2 minus pi over 2. Now if I just factor out the pi over 2, then what's in here is going to be a minus 1. a squared minus 1, I can write it difference of two squares, a plus 1, a minus 1. A minus 1's cancel, and what we have for our general formula is going to be pi over 2 times a plus 1, and that's it. So now back to our original problem when we had 2025 in here. We just need to take 45 and plug it in here. And so what that's going to be is going to be pi over 2 times, this becomes 46. And so for this solution, we just get pi over 92. Okay, so there you go. Apologies to Ashish. I know I did the wrong problem. I'll look into your problem and see. I don't know if I can do it with arctemp, but I'll at least give it a shot. Thanks everyone for watching. Have a good day.